Okay, hello everyone. Welcome back here. Now let's talk about how do we calculate the total amount heat given off or absorbed? How do we calculate Q by a substance? Um, if we were to, transfer heat from one substance to another. Okay, so in this case, we have to define the symbol that we use for change in temperature, right? So usually we use a triangle called delta, so the capital D letter for delta in the Greek alphabet, delta T. So that means the change in the temperature, okay? So let's write that here. Delta T means change in temperature. Okay, so usually when we find a change in temperature, we have an initial value and a final value, right? So the change in temperature is always going to be a positive value, so no need to make it negative. Well, sometimes no, it can be negative, okay? But we usually say it's T final, our final temperature, subtracting from our final temperature, the initial temperature, okay? So we use this equation here: T final minus T initial. Okay, so in these questions, it'll be helpful to label all your variables so you kind of know how to put it in the final equation. Okay, so what will we need for our final equation here? Okay, so to calculate the heat absorbed, we have this equation: Q equals N C subscript M delta T. So this is using moles. If we were to use moles in our calculation, okay? And this one is using grams. So CM stands for molar heat capacity. CS stands for specific heat capacity. Okay, so using moles, we use the molar heat capacity. So we just call it molar heat capacity. We don't call it specific molar heat capacity because there's only one molar heat capacity, and that depends on the number of moles. But for grams, we use the specific heat capacity, and that's when we define grams in our equation there. So specific heat capacity. Oops. Okay. All right. So Q is the heat that is transferred or absorbed between objects, substances, matter, right? C, depending on what your heat capacity you're using. If you're given moles, use the molar heat capacity. If you're given grams, use the specific heat capacity. So it depends on what you're trying to find, right? So don't. So the nice thing about these kind of calculations, you don't necessarily need to convert from grams to moles, but I won't say you will never need to do that. It really depends on what you're trying to find. Okay, so now let's do an exercise here. How much heat would have to be absorbed to raise the temperature of a 500 gram iron bar from 25 degrees Celsius to 50 degrees Celsius? Okay, so one thing I want to point out: temperature, you don't have to convert it to Kelvin. You should just use the temperature unit you're given. So the units for heat capacity, they could be Celsius or Kelvin. So just use the unit you're given, the temperature unit you're given in. Okay. All right. So the first thing you should write is your equation. Don't just simply plug in numbers. On an exam, you won't get full credit. Okay. So I will take like 1 to 3 points off for just not showing, your complete thought process here. So Q. So first, write equation. Q equals. So we have our mass is given in grams. So let's use the mass times CS times delta T. Okay. All right, so now we can just plug everything in here, or if you want to list things first, that probably might be a little bit better. So the change in temperature is, all right, so the change in temperature is the final minus initial. So T final is 50 degrees Celsius, so 50 degrees Celsius minus, and you see here, initially the bar was at 25 degrees Celsius, so that's going to be our initial temperature. Okay? All right, so that gives us a change in temperature of 25.0 degrees. Okay. Our mass here is 500 grams. So let's just assume this is 3 sig figs, 500 grams. And then our specific heat capacity. So you may be wondering, oh, what if our object is a mixture of metals? Well, in that case, you have to find the average. Well, not the average. Yeah, you'll have to find the, not the average, but the relative. You'll have to kind of find the geometric average of the specific heat capacities based on the percentage of each metal. Say that you have an alloy, so like, you know, most objects, they're usually like a mixture of metals. It's not usually something pure, but we're making it simple here, so it's going to be a 100% iron bar. So if we look back at our table here, we see iron is 0.449 joules per gram Kelvin, but we know that, remember, it doesn't matter if it's Kelvin or Celsius, the value of the specific heat will be the same. So we can just translate this to 0.449 joules per gram degrees Celsius. Okay, now let's plug everything in. So now we say Q equals 500 grams times the specific heat here, 0.449. So let's just put this as a fraction here. Joules per gram dot degrees Celsius. So maybe let's fix this too. Okay. And then we should multiply by the change in temperature, 25.0 degrees Celsius. Okay. All right. So now let's see what units cancel. Celsius is on numerator, cancels out in the denominator. Grams cancel out the denominator, and what we're left with is joules, energy. So when we do this calculation, we get 5.61 times 10 to the third joules. So that's our final answer. Okay, so there we go. So that is our final answer here. Okay, there we go. So that's how we would solve a typical specific heat capacity problem. So one thing I want to kind of stress here is that you label all your variables. Don't confuse, where to put the values. So it's kind of important that we do these problems in class and then we go to discussion and work on more detailed problems, because the problems in discussion are more representative of what you'll see on the exam, especially for free response questions. Okay? All right. Let's try part B. All right. So the 500 gram iron bar at 50 degrees is placed into 500 grams of water at 25 degrees Celsius. If the iron bar loses 5.1 times 10 to the third joules of heat, what will the final temperature of the water be? Okay, so this problem's a little bit different. So you now have the value for Q, which is 5.1 times 10 to the third joules. So we want to figure out what's the final temperature of the water? Okay, so so what we can say is, so let's talk about first the energy. All right, so the iron bar loses 5.1 times 10 to the third joules of energy, right? So what does that look like? Well, we could say negative Q. Remember, negative Q means heat was lost. Negative Q, iron, equals the energy that was absorbed by the water. So that's going to be the amount of energy absorbed from the water. So the water is going to get, so Q H2O equals 5.1 times 10 to the third joules. Okay? So now we can plug that into our equation here. Q equals mCs delta T. Okay, so now we plug in 5.1 times 10 to the third joules here equals the mass of water is 500 grams. So we're going to put 500. Okay, and now we go back to the specific heat of water is 4.18, or you can use 4.184. Does not matter to me. 4.18 joules, grams, degrees Celsius. Okay, now let's move this over a little bit. Okay, and then times the change in temperature. We see here the initial temperature is 50. Well, actually, no, sorry. So we're talking about the water, right? So the initial temperature was 25. We're trying to figure out what the final temperature of the water will be. So we're going to put in, we know change in temperature is equal to T final minus T initial, right? So we could just put that into our equation here and substitute T initial for 25 degrees Celsius. Okay. So the one problem I see with students for this question is that they sometimes confuse how to solve for T final because it's addition subtraction. So they think they could just divide everything, but that's not the case here. You need to isolate the last term, TF minus 25, by itself first, and then you can solve for T final. So I'll go over that. So change in temperature, T final minus T initial. Okay. All right. So what we can do is we're going to divide both sides here by 500 grams times 4.18 joules, grams, degrees Celsius. Okay, so this will cancel out, and this will cancel out. And we divide the same thing right here. Okay, so what we get is, so what we do get is approximately 2.4. Well, let's let's just simplify it. It's okay. 2.4 equals, not equals though, but yeah. So if we simplify this, we get 2.4 equals T final minus 25 degrees Celsius. And then if now we can isolate T final here, and T final should equal 27.4 degrees Celsius. Okay, but let's just double check that here. So we are so we're not rounding prematurely. So 5.1 e to the third divided by 500 divided by 4.18. So let's just keep a few extra digits here. Just say 2.444402. 4402. Okay. And then once we add those two terms here, we will get an expanded decimal here. Yeah, so we get 27.4402, and then we could round that. In this case, since we're adding here, we want to round it to 1 decimal point. So let me just put this in its proper term here, 45.0 degrees Celsius. So the two values here, the t initial only has 1 decimal place, so we should round it to 1 decimal place. So 27.4 is our final answer. Here we go. Okay. So that's how you would do that problem. So we can ask you like what the final temperature sign will be, like or what the initial temperature was. So there's a lot of ways we can phrase this question. But it's just using the same equation. We're just rearranging it differently. So let's see if all these units cancel here. Yes, they do, right? So joules cancel, joules, grams, and then grams cancel. And then what we're left with is a degrees Celsius unit. So degrees Celsius would cancel there, and that's our answer. Okay, so let's move on here. Okay, so that's a typical specific heat question. Now, we'll see some types of these questions. It won't be this simple. It may be, but usually we want to use these types of equations for a chemical reaction. So it'll have an added layer of complexity. All right, now let's talk about state functions. So you may have heard about state functions in your high school chemistry class or another chemistry class. So state functions, just like the name implies, we'll talk about exactly what they mean when we get to it here. Okay. So basically, let's talk about some properties. So every system, we can describe them in terms of certain properties that can be measured in the lab. For example, a gas can be described in terms of the number of moles of particles it contains, or subscript N. Symbol N. Its temperature, T, pressure P, volume V, mass M, or its density D. Okay, so these properties describe the state of the system in a particular moment in its time. So some properties depend. Some properties depend on the size of the sample. Okay, such as mass and volume. Right, because the mass of something depends on how much you put on a scale, right? The less mass you have, the lower the amount of substance you have, and the more mass you have, the more substance you have, right? And then volume, the less of a substance of a liquid you add, the less volume it occupies, and the more liquid you add, the more volume it occupies. So we call these extensive properties. So extensive property means that no matter what the value of, it depends on the size of the system, right? Right. So when you measure out the mass, right, it depends on how much you measured out or how much volume you measured out. So it depends on the size of the system. So other properties such as temperature and density, they don't actually depend on the size of the sample being studied. And we call them intensive properties. So intensive properties are pretty much measurements that don't depend on the amount of substance that's being measured. So for example, if you measure the density of water, right, it'll be the same for 10 milliliters of water versus 1 liter. So you take 1 liter of water, it's still water, right? So it's going to be the same density as water. And you take 10 mils of water, still water, so it has the same density. So temperature too, right? So think about the temperature. If I took the temperature of if I took the temperature of 1 mil of water, so let me put it this way: the temperature of 1 milliliter of water and the temperature of 10 milliliter of water, they'll be the same, right? It doesn't matter how much you have. I mean, if you have 1 milliliter of water versus 10 milliliters of water, they'll have, when you measure the temperature, they'll still have the same temperature at any moment in time, right? So you take 1 milliliter of water at room temp, take another room temp measurement of water at room temp. There's different sample sizes, they have the same temperature. Now, what's different is how long it takes to get to that temperature, right? So 1 mil of water, it may take a shorter amount of time for 1 mil of water to heat up versus 10 milliliters of water to heat up, or a liter. And that has to do with heat transfer. And heat transfer is, or heat is not a what we call a state function. So we're going to go talk about state functions now. So properties can also be classified as state functions. Okay. All right, but first let's fill this out. They're called intensive properties. Yeah. Oh, I was supposed to write properties here, so let's just say properties. But maybe let's write it smaller. Yeah. Okay. All right, let's end this video here, and in the next video, we'll talk about state functions. Okay, so I'll see you then.